Welcome and thank you for joining. Let's take a look at a couple of examples where we practice how to use the second derivative of a function to determine its concavity. So in example number 3, we have y equals x4 plus x3 minus 3x squared plus 1. We're going to start off by finding the first derivative. So it's simply power rule, so we go 4x to the power of 3 plus 3x squared minus 6x, that would be the first derivative. And the second derivative is f second x equals 12x to the power of 2, again power rule, plus 6x and then minus 6. So to find the key values, which are potential points of inflection, we make the derivative equal to 0. So the second derivative f second x here would be 0, which means that we have to solve the equation 12x squared plus 6x minus 6. So I would divide all the terms by 6 since it is a common factor for all the coefficients throughout the equation, and that will make the equation in a more simplified form easier to factor. So we have 2x to the power of 2 plus x and then minus 1. So next, we would like to solve again. So we go 2x. Let's see if we can factor. If it is factorable, it's kind of nice. So plus 1 and minus 1, see if it works. So 2x squared, positive 2x and minus 1x will give x, which is the middle term, and minus and plus 1 multiplied give negative 1. So we're good to go. So we're going to say that the key values are at the zeros of the second derivative, which means that at the points 2x minus 1 equals 0, where x equals 1/2, and at the point where x plus 1 equals 0, which is at x equals negative 1. So let's take a look at the chart that we use to discuss the sign of the first derivative. So we have the domain of the function, which is from negative to positive infinity. It's a polynomial function. And we're going to list the key values, which are at negative 1 and positive 1 over 2. So negative 1 comes first, positive 1/2 here. And if you wish, you can list the factors separately, or you can simply write down the derivative, the second derivative, which is, by the way, let's be consistent again with the notation. F second x is 12x squared plus 6x minus 6. So the sign of the second derivative will help us describe the shape of f of x. Our f of x is x to the 4 plus x cubed minus 3x squared plus 1. So the derivative will be 0 at x values of negative 1 and 1/2. And in between, we have to discuss the sign. So you can pick a number anywhere from negative infinity to negative 1. And then sub it into the equation of this function to find out what the sign of the expression will be. Or you can simply look at the equation of the second derivative. It's a quadratic. The leading coefficient is positive, which tells us that it will be a parabola that opens up. So a parabola that opens up will pass through the zeros, which tells us that between the zeros, the graph of the derivative will be below the x-axis, so the y values will be negative. And to the left of the negative 1 and to the right of 1 over 2, the values of y would be positive. So this tells us that the graph of the function will be concave up, and then concave down, and then concave up again. So since concavity has switched at the key values, that means that the points at x equals negative 1 and 1/2 will mark points of inflection. So there will be a point of inflection at x equals negative 1 and another point of inflection at x equals 1 over 2. So if you are asked to find the coordinates at the point of inflection, that what we want to do is find f at negative 1 and f at 1 over 2. And at negative 1, you will have the value of the function -1 to the 4 plus -1. So here is the equation actually, so you can follow from here. -1 power of 3 minus 3, -1 squared, and then plus 1. So here we go. We have +1, -1, 0. -3 times +1, -2 plus 1 is -2 here. So the y value will be -2. When x equals a 1/2, you simply use a calculator in here, especially if you're writing a test, so you want to save your time. And write the final answer always in exact form. When we list the coordinates of a point, we want to list them in exact form. And what we get in here is 1/2 to the power of 4, which would practically be 1/16, plus 1/2 to the power of 3, which would be 1/8. And then -3 times half squared is 1/4. And then plus 1 at the end. So I got a decimal value here on my calculator. So I will convert it to a fraction. So 7/16 or equals in decimal form, which in this case happens to be an exact value 0.375. So if we looked at the graph of this function, so if we were to draw the graph on decimals, so let's take a look. So what we have in here is y equals x to the power of 4, and then we had minus 2x to the power of 3, I think, and then minus 3x squared, and then plus 1 at the end. Let me just double check. Okay, so a typo here. So let's take a look at this. So we had plus x3 minus 3x squared. Okay. So that's a plus x to the power of 3 and minus 3x to the power of 2. So here goes the graph of the function. As you can see, the function will have or will start concave up, continue concave down, and then concave up again. I want to discuss something else as well, so just bear with me for a second. Okay, so let's copy down the graph so we have all our notes together here. So as you can see on the graph of this function, we start off with a concave up shape. Okay, and then at x equals -1, we have a point of inflection. And then continue with a concave down shape. And at x equals at x equals 1/2, we have another point of inflection, and the graph goes all the way up, maintains the same concavity. All right, so another thing that I wanted to actually show here, since we're talking about the second derivative, so how do we determine whether the second derivative is positive or negative using decimals? So what you want to do is draw the graph of the function first. So type up the equation of the function, and what I would do as well is write the equation of the function, oopsie, name it by using the letters of alphabet. So I'm going to name this f of x, and then go down here and go to functions. It looks different on the computer, on the laptop, and a little bit different on your phone. So take the derivative, and then since we're looking for the second derivative, so you have to type the derivative again one more time. So d dx of d dx, or the derivative of the derivative of, and now we type the name of the function we are differentiating, so f of x. Now, as you can see in here, and I'm going to silent the equation of the function. As you can see here, the zeros of the derivative are at -1 and 0.5. And you see that the derivative between these two values will be negative below the x-axis. This is the graph of the derivative, right? And on the left side of -1, we'll have positive y values, and on the right side of 0.5, also positive y values. So just in case you want to check the answers when the answers on the textbook do not match the answers you find, this is how you can use Desmos to double check your answers. Okay, so you have another example that I've asked you to do on your own. Let's do this very quickly together. So we are trying to find or discuss the concavity of this function. So we have y equals x4 minus 6x squared minus 8x. We'll start with the first derivative, dy dx equals 4x to the power of 3 minus 12x and then minus 8. We need the second derivative to analyze concavity, so that would be 12x squared minus 12. We'll make that equal to 0 to find the key values or the potential points of inflection and solve for it. So 12x squared will be equal to 12, so you can take the negative to the other side and rewrite the equation with variables on one side. So it's a simple, actually, manipulation of this algebraic, equation. And we have x squared equals 1, which means that x can be either positive or negative 1. So there are two key values which will mark potential points of inflection. And we say potential points of inflection because we have to check and see whether or not the concavity is changing around these points. So we have negative to positive infinity for the domain of the function, and the two key values are at negative 1 and positive 1. dy dx is a third degree. The second derivative is second degree, so we'll write that down here. So 12x squared minus 12. And we'll decide on the nature of function y down here. And let's drop the zeros first. And as you can see here, we have a quadratic. The leading coefficient is positive, which means that this quadratic will open up. So the graph of the derivative will be parabolic that opens up. So in between the zeros of the second derivative, we see that the graph of the derivative is below the x-axis, which makes this negative, and the y values will be positive from negative infinity, negative 1, and 1 to infinity. So this tells us that the graph of the function will be concave up and then concave down, concave up again. As you can see around the key values, the concavity is changing from up to down and then from down to up, which marks the points at x equals negative 1 and positive 1 as points of inflection. So if we want to find the y coordinate again, so what we want to do is find the value of y at each x. So at x equals 1, we'll have 1 to the 4 minus 6 times 1 squared minus 8 times 1. And that would equal 1 minus 6, negative 5, minus 8, negative 13. So we have y equal to negative 13 here. Okay. And at the x value of negative 1, let's see what we get there. So y at x equals negative 1 will be negative 1 to the power of 4 minus 6, negative 1 squared minus 8 times negative 1. So that will make a positive 1, minus 6, negative 5, and negative 5 plus 8 will be positive 3. So the y value here would be equal to positive 3. And voila, here we are. We have 2 points of inflection. And the function will have a concave up shape for the x values from negative infinity to negative 1 and from 1 to infinity. The function will have a concave down shape for x values between negative 1 and 1. Remember not to include the ends of it because we're talking about the concavity. And concavity means, concave up or concave down means that the function has to be either positive or negative and that the points of inflection derivative is 0. So the ends of the interval are points of inflection, so they are not part of the concavity. So I hope this made sense, and I hope you found it useful. Bye for now.